And today I want to talk about molecular spectra. So, okay, last time we started talking about the simplest molecule, which was something like H2, for example, which you can think about it like some kind of like a dumbbell, right? We started with like an H2 ion, but later we said we can also put one more electron and we can talk about the H2 molecule without ionized form. And there are like different things we can do with this, and each different thing we can do with this is going to correspond to a result in the spectrum. And that's what we call molecular spectra. First, of course, one thing we can do is there are several, let me call these excitations. So what this means is like there are several ways you can deform the system. There are several ways you can increase the energy from the minimum ground state. So several excitation, let me call it modes, to expose you to jargon. So one is, of course, you can break an electron out of this, like there's like electronic excitation. Electronic excitation, right? It doesn't have to be H2, it can also be other molecules. You just go there and there's like this complicated system, you just take one electron out of it. That's what electronic excitation is. And from our understanding of like atomic physics, we know it should be like, what is the order of electronic excitations? What is the key number? We know about, it is the n square, but the scale of energy. 13, right? Something like 10 electron moles. That's what we should think about this. So electronic excitation is about 10 eV, 13.6 if you want. But different molecules have different levels, but it is like, say, if it's not 13.6, it's like, I don't know, 5, maybe, I don't know, 4, something like that. Of course, like also, you should also remember, like there is also like a mode, like you can break this bond. Like for example, you can break up the molecule. I think last time we considered, for example, breaking up like an H2 molecule, which in its ionized form, we found it to be something like 4.5 eV. But we are not going to consider breaking up the molecule. There is like a composite object. Protects its form, but it can increase its energy in various forms. And the first one is electronic. And the second one is vibrational modes. So what we think about molecule is, of course, there's like some complicated potential, which I'm going to come back in a little bit. But like roughly speaking, we can think about a dumbbell, but connected with like a spring. And because of these excitations, right, this is like a harmonic oscillator. And if there's like a harmonic oscillator, you can quantize it. When you quantize it, there are going to be energy levels. And this system can go from one energy level to another. Normally, it's in its ground state, but you can increase it by external means. And the energy, so this one is, by the way, this is, for example, corresponds to visible. And this one has energy scale of order like 10 to minus 1 eV, like 0.1, like maybe 100 times smaller than electronic eV, and it corresponds to infrared radiation. So we cannot see infrared, but if you have the infrared camera, you look anywhere, you actually see this mode, basically. Because it's like wavelength is like what? It is 1 micrometer to about 0.1 millimeters. And the last one, okay, this is the kind of dumbbell we are talking about. What is the last thing we can do with this to increase its energy? Any other means we can put energy in this simple system? Huh? Yes, exactly. There's like rotational mode. There's like some axis of rotation, and you can consider rotational modes, which we are going to be also giving details, but this one is even smaller. This is like order of 10 to the minus 3 eV. And this one corresponds to, for example, microwave radiation. Okay? We don't use microwave ovens too much in this country, but that's the principle. There's like some molecule, like, for example, water is a molecule, and you put it in the oven and send the radiation with the right frequency. You are going to put energy inside, and the right frequency in this case turns out to be the microwave. And you, like, if you are an engineer, you just go and find ways to generate microwave in like a container, and then you make a lot of money. Good. Any questions? So let's talk about this very briefly. All we need, we already know, right? Basic quantum mechanics. And I'm going to tell you how to do that, and then that will be the end of today. So let's start with rotational levels. So let's consider diatomic molecule. I mean, we can also consider more complicated molecules, but the basic idea can be obtained from the diatomic molecule. And what we have is like this object. So let's keep it general. Let this be mass m1, this one m2. There is some rotation axis, which is center of mass. And the code here. You can see that, right? Okay. And the moment of inertia of this object, okay, moment of inertia. What is the moment of inertia of a dumbbell like this? There's like, suppose this is R1, this is R2, mass is M1, M2. We use I. But this is like two different masses, right? Point masses, if you want. This is M1 R1 squared plus M2 R2 squared, right? Simple stuff, just the definition of moment of inertia. But you can, for example, okay, here's your exercise. You can show this to be equal to reduced mass times center of mass squared, right? So that's also the same. So just try to come up with reduced mass and try to come up with center of mass and take the square, and you are going to obtain this one. So let me not do that to save some time. If I know the angular moment of inertia, I can write angular momentum. So classical angular momentum is L I omega. This is the baby angular momentum. So that's all we need. And if you want to quantize it, so what is the quantized version of angular momentum? L? Exactly. H bar. So this is quantize. Let me open up some space. H bar. We use the letter J for this. J plus 1, right? And this is in line with our motto. Any angular momentum is an angular momentum, and they all have the same form. Whether you have orbital angular momentum, which is L, whether you have spin angular momentum, which is S, or rotational angular momentum, you have there's only one way to quantize angular momentum, and that's it. If I have the angular momentum, I can consider energy. What is the energy in terms of angular momentum? This is a first year question, freshman. If I give you angular momentum and moment of inertia, how do you write down the total energy, which is only kinetic energy, right? There is no potential. L squared divided by 2I. So it's kind of like a mystery to me why this formula is so confusing. It's just p squared over 2m, right? Replace p with l and replace m with I. That's what it is. Is that clear? And if this is L squared, we know how to quantize L. We just put this there, and this is going to be h squared over 2I j plus 1. J is angular momentum number. It can be 0, 1, 2, ... infinite. And these are rotational energy levels. And now, like, here's the levels. Like, this is J is equal to 0. If you put it like this is E is equal to 0 in units of h squared over 2I. Maybe there's another one here. J is equal to 1. And E is going to be equal to 1 times 2 is E is equal to 2 in units of h squared over 2I. Maybe there's another one here. Actually, let me write 2 more to show you the full pattern. So there's another one here. So this is J is equal to 3, and E is going to be equal to, 2. 2 times 3 is 6 in units of h squared over 2I, and last one is J is equal to 3. Of course, there is more, but I'm not going to write. And 3 times 3 plus 1 is E is equal to 12 in units of h squared over 2I. And typically in molecules, we see the absorption, right? So you have like a molecular gas, and you send the light, and the missing part of that light is going to tell you about these vibrational modes. That's what we call the absorption spectrum. And for this kind of molecule to absorb light, so to absorb radiation, so what do we need to absorb radiation? Classically, right? So we need exactly the same thing to emit radiation, right? To emit the radiation, we need what? We talk about this a little bit. Classically, if you use the classical electricity and magnetism, Exactly, right? There has to be some charge acceleration, and the charge acceleration, we generally put it inside so-called like electric dipole. If you need the electric dipole, right, we calculated the expectation value of x, and we said if that's non-zero, it's like we build a selection rule based on that, right? And the conclusion, in brief, is like you need to have like an electric dipole to emit or to absorb radiation. So to absorb radiation, we need electric dipoles, which unfortunately H2 doesn't have. So you only can do this with molecules which have like a non-zero electric dipoles. And these dipoles are going to give rise to selection rules. And selection rule is what? You have to go from one state to another, and it has to have like delta J is equal to plus or minus 1, right? Because the light comes out with an angular momentum. You don't have a light without an angular momentum, right? Then for you to have an absorption of a light, you need to have this selection rule. And the absorption generally goes from some J1 plus 1 to J, or like, okay, we are talking about absorption. So it is like J goes to J plus 1. So basically you have some, okay, now, up until now we were thinking about electron being on a level. Now we are thinking about a molecule being on a level, right? This is kind of like an abstract representation. When we put a dot here, that means molecule is in that level. And by absorbing light, molecule can go to J is equal to 1 from J is equal to 0. And you can see selection rule is obeyed. And if you look at the, like this is the spectrum, you look at the nu, there is like a, for example, this one is energy difference is 2 minus 0 is 2 in units of h bar squared over 2I. There is one line. Another possibility is I can go from level 1 to level 2, right? I have the same selection rule obeyed. I'm good. The energy difference is like 6 minus 2 is 4. So this is mu is equal to 4 in units of h squared over 2I. Or I can go from j is equal to 2 to 3. Selection rule is good. Energy difference is 12 minus 6 is 12. And so on. So what we see is in the spectra, we have like equally spaced spectrum. So it's like a typical from like a molecular spectra. And like, for example, if you have like a molecule and you want to determine the moment of inertia, you can look at the like a vibrational spectra, and from the spacing, you can just extract the moment of inertia, right? All you need is Planck's constant, and then you can get it from your from your experimental result. Any questions? So this we said is like order of what? This is rotational levels are 10 to the minus 3 eV. So all of these, something like 10 to the minus 3 eV. So now let's look at the next one. The next one is vibrational levels. So if you remember last time we said here is the total potential, right? The total potential had like again, I am thinking about the simplest model we can think about, like H2 molecule, for example. There is like some distance, and as a function of distance, and this is the total energy of ion-ion interaction and total kinetic energy of the electron. Electron can be here or there, and there's like a energy scale for that. And we said if R is very small, we are going to blow up because these two ions are going to repel each other electrostatically with Coulomb, and 1 over R, which is Coulomb, is going to blow up as R goes to 0. And you are going to decrease. And if R goes to infinity, you are going to converge to a constant, which is like minus 13.6 for our simplified model, but other molecules can have other levels, but it's going to be something like that, right? Just because of the existence of the molecule itself, I know there has to be a minima like that, right? If there is no minima, there is no molecule. And this, generally, this is like a complicated potential, and even for 1 over R, remember how much pain we had to go through to solve it. So this one is not solvable, but what we can do is we can approximate it with a harmonic oscillator. Like there is like a harmonic oscillator here. What this says is like take this V and Taylor expand around this. Like there's like a global minimum, like let's say R naught, and you just expand it around here. Like so. Okay, let's use it. V of R is approximately equal to V of R naught plus some constant, which I'm going to allocate spring constant for that, R minus R naught squared. So this is overall constant. We can drop it, and here is like a harmonic oscillator. And now we know the solution of this, right? The solution is like, there is like classical frequencies, omega is equal to K over M. M is reduced mass, but let me not write it, right? Like we are thinking about this molecule being connected by a spring. But by changing the reference frame from like this to like center of mass frame, we can think about a mass which is connected to a wall, but M is M reduced, right? So we can change from like global coordinates to center of mass and relative coordinates, and we can do this for any two-body problem. And this is the reduced mass here. And once you give me the frequency, like once you give me the spring constant, which is coming from the potential, I can calculate the frequency, and also I know the mass of these individual constituents. Then I can find the energy levels. And energy levels are simple harmonic oscillator, which is h bar omega n plus a half, and n is going to be 0, 1, 2, dot, dot, dot. So you can see there is always like a ZPE, there's like a 0 point energy for n is equal to 0, and that's due to uncertainty principle. We cannot put this exactly there, right? There has to be like a jiggling from the laws of quantum mechanics. This is due to Heisenberg uncertainty. And also there is like a selection rule, right? So now the same logic applies. For us to emit or absorb radiation, we have to do this like accelerating charge argument over and over and over again. And if the charge needs to do that, that means this spring has to oscillate, right? And that means it oscillates with the frequency omega. So this is like an oscillating dipole with omega. And it is going to emit a radiation with omega, right? And that means radiation with omega. And that is going to mean there's like a selection rule, delta n here, which is the quantum number. We used J previously. Now for the vibration level, I use n. It should be plus or minus 1. So a little detail, I think that needs to be, we need to be careful. Maybe I can pose this as a question to you, and you can discuss it with your friends, or you can read the book. So it seems like equal spacing from the harmonic oscillator analogy, but we know this entire thing is not harmonic oscillator, right? At some point you can see there is like a deviation between our approximation and the real potential, and here too, right? At some point there will be some non-negligible deviations from harmonic oscillator, right? Especially you come to this level, and the question is, so this is equal spacing. How does level spacing change for higher energy levels? Okay, does it increase or does it decrease, and why? What is the logic? And a hint for you is like think about anharmonic contributions. I mean, this is like sounding fancy, but you just consider the fact that there's like a difference as you go to higher energies. So the energy scale for vibrations is like what we said here. So we outlined there's like electronic first, and then vibrational, which is like 0.1 eV, and there's like rotational modes, right? So if you want, we have these vibrational modes. Maybe I can do it like this. So we have, let me draw it like this. Hopefully you can see. So first there are these so this is V of R, this is R, and we have this you want this level due to ground state. Suppose I take this molecule, right? There is like I take this molecule and I excite one of its electrons. Like there is like an electron wants to go to like smallest possible energy, but I can imagine to increase it, right? what is going to happen is like electron is going to just increase its energy, but molecule is doing what molecules does. So the whole thing is going to be just shifted a little bit, right? So I just need to take this, and right, I need to do it, shift it like that. So this is electronic, what I call electronic ground state. Right? All electrons are in the smallest possible state. That's electronic ground state, and this is electronic excited state. So I think I can erase this. Excited state. And for each one, so this spacing is like order of 10, right? So this spacing is the largest spacing, right? It is the largest energy scale in our problem, and it is order of like 10 to 20 eV. And the next thing is like these, like there are like these harmonic oscillators in each valve, right? And there is also, okay, maybe I can use another color, not to mix up. So there are like these harmonic oscillators here. Maybe I can just draw 3, and there are also harmonic oscillators here, 1, 2, 3, and the spacing here is order of 0.1 eV, right? 10 to minus 1 eV. And inside each level, there are these vibrational levels, right? They're like little tiny, and these, right? And many of these, right? And these are 10 to minus 3 eV. So these are rotational levels. And that means if you are working with molecules, you have to consider all of these levels to do what you want to do, right? To get what you want. For example, if you want to get a microwave, right, you have to think about this 10 to minus 3 eV scale, and you convert that eV to like a wavelength, so you go and think about microwaves. So let me just give you a couple of applications that you may have heard here and there, and explain where they comes from, and then finish it there. So one thing is like very common, is so-called fluorescence. So in the case of fluorescence, okay, let me try to copy this. So you have something like that. So it is like, I don't know, I think we don't have them anymore, but in the past they used to be very common. So you have like a gas of, I'm not 100% sure, but it is, I think I didn't write it here. I think it's mercury and argon, right? You pass like a electric charge through a gas of mercury and argon, and then they collide, they do whatever they do, and then they emit UV radiation. But what you do is, okay, here is the kind of like the picture. So there's like a tube, which is, for example, your lamp, and you have these gas molecules, and you pass these currents, you pass high voltage. What this means is like you pump energy, and these guys are going to be excited, and to return to their ground state, they emit UV radiation. But what you do is you also put some coating on this material, on the walls, which is the white stuff. I don't know if this generation can see these lamps anymore, but they used to be very common. And I think this is like a phosphor coating. And what happens is like, okay, you take this phosphor, like it's like a molecule, in a molecule form in your material, and you take it from here. It is, okay, unfortunately I didn't get the second level. So let me try to copy it one more time. So this thing, erase. I need to get the entire thing. Okay, hopefully, yes, now I got it. So what you do is you take this molecule from its ground state and you excite it with this UV to, I don't know, somewhere over here. One of these like green molecular levels, right? But what happens is like over time, all kind of things happens which you may or may not control, and these molecules slowly transitions from one level to another, and eventually it's going to emit, right? It doesn't want to go, it doesn't want to stay in that higher excited state. So you send it a UV, which is not visible from this mercury-argon mixture. It just slowly rolls down all these levels and goes to another level, and eventually it goes to ground state like this, and this is the visible. Okay? And that's what we call fluorescence. I think some fabric softeners also have that, right? Sometimes you buy like some cheap detergent, and then every once in a while it just glows and you get surprised, right? I think something similar happens for that too. Another thing is like phosphorescence. Phosphorescence. So what I said to you was like this, like I have like these levels. But, let me draw it one more time. Maybe a little bit nicer to see to show you the important structure. I have, so this, I have this molecular potential, and I want to duplicate it. So this is my electronic excited state, and sometimes I have, like, we show it like this. So sometimes the electronic excited state can have like a spin structure. Like, for example, so this is, the first one is ground state, electronic ground state. So this is a singlet excited state. What this means is electron in a singlet state. I think you don't need to worry about it. Just imagine like an internal structure. And this one is triplet, right? And typically you don't go from singlet to triplet, right? You have all these levels here, you have levels here, and you have these levels here, and also the triplet also has levels. You can see the energy levels of singlet excited state and triplet excited state kind of like come close. Anytime they come degenerate, you have a chance to go from one to another. So what you do is, for example, you put that material in sunlight, and the molecule goes from, I don't know, from here to there. Most of the molecules want to go back to their like ground state. They emit whatever do, but every once in a while, some of them are going to transition from this black line to red line. And this from that line, maybe they are going to roll over the hill, but they are going to be trapped somewhere over here, right? Now this is a triplet, and you cannot go from triplet to ground. Of course you can go, right? It is happening, but it happens in a longer time scale. So what happens is like it stays here for minutes, and you take this in a dark room, right? Like there's like this excited state in your material. It stays for minutes. It doesn't stay for like years. At some point it has to, it wants like, there are like many molecules in your hand. Some of them are trapped in that minima. Eventually they are going to go, and like that's what you are seeing. Like this is the phosphorescence. Okay, I think I'm going to stop here. Any questions or comments? This is all I want to talk about this chapter. Next week I'll start the new chapter. Good? Okay, thank you.